Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Electronics Honors for the subject Analog Electronics. So, these are the contents we are going to discuss today. Derivation of gain, input impedance and output impedance for the remaining feedback circuits, practical feedback circuits, voltage series, current series and voltage shunt feedback, and phase and frequency considerations, in which Nyquist criteria, Nyquist plot, gain margin and phase margin we are going to discuss. This circuit is a voltage shunt feedback network. Here the voltage output voltage is taken as the input of the feedback network and it has been given in shunt to the input current source. So, it is a voltage shunt feedback network. So, here the input is the current source Is, output is voltage, and if you see the gain of the total circuit, gain with feedback AF, it is V naught by Is. So, the overall gain, it is V naught by Is, and V naught can be calculated from the gain of the amplifier as A into II. So, AII by Is, it is the summation of the input current, or you can derive what is Is here. It is the current flowing through this node and these two currents are away from the node. So, Is can be given as If plus II. So, it is II plus If, and AI by here If is the feedback current. So, it can be given as beta V naught. So, you can replace this If as beta V naught and finally take I1 out, and you can neglect, you can cancel out this I1 term. So, it is AF is equal to A by 1 plus beta A. This is the overall gain. So, when you compare the overall gain with the gain without the feedback, it is the gain without the feedback is reduced by the factor of 1 plus beta A. So, whenever you are calculating the gain of any feedback circuit, the gain will be reduced by the factor of 1 plus beta A. And the next is input impedance with feedback for the same circuit, voltage shunt feedback. So, when you see the feedback network, the type of the feedback network itself, you can say the input impedance is reduced or not, or increased or not. It is a voltage shunt feedback. So, you have to give shunt connection to the input side. So, if you have a shunt connection at the input side or at the output side, the resistance value will be reduced. So, here it is the connecting shunt to the input current source. So, the overall input impedance will be reduced. So, how the impedance is reduced now? It is the overall input impedance ZIF is given as Vi by Is, Vi by Is, and Is can be written as, according to the Kirchhoff's current law, it is II plus If, and If is replaced by beta V naught from here, and beta V, when you divide both the numerator and denominator by II, this term will be cancelled out. So, it is 1 here. Vi by II can be taken as Zi without feedback, and here this V naught by II can be taken as the gain without feedback. So, Zi by 1 plus beta A is the overall input impedance, and when you compare the overall input impedance and the impedance without feedback, the impedance without feedback is reduced by the factor of 1 plus beta A. So, it is reduced. We know that from the name itself you can say that it is a shunt feedback. So, the shunt type of feedback will reduce the input impedance. Even it is the same for the current shunt feedback, because it is again a shunt connection at its input. So, the overall input impedance is reduced by the same factor 1 plus beta A for current shunt feedback. So, here you have seen the input impedance. How will you obtain the output impedance, and what is the case for output impedance, whether it is reduced or whether it is increased. So, when you look at the again the name of the feedback, it is voltage. How will you take the output voltage from parallel connection? So, if you have a parallel connection in either side, whether it is an input side or an output side, the parallel connection will reduce the impedances. So, here the voltage is taken parallelly, so the output impedance is also reduced. The overall input impedance of the feedback amplifier will reduce due to the parallel connection of the amplifier. So, if the input impedance is small, then the input source must be a current. For an ideal voltage source, the input resistance is very high compared to the internal resistance. If not, then lot of voltage will be dropped at internal source resistance, and voltage source won't be a ideal voltage source. That is the reason if the input resistance is very small, we will have a current source. So, why we have a current source for the shunt feedback network? Because the input resistance is very low. So, if it is low, then we cannot use a voltage source. If we use a voltage source for a lower resistance, then lot of voltage drop will be there across the input impedance. So, it will not be a ideal voltage source. So, we are going for current input source. If we have input resistance low, the effective output resistance is also small compared to the resistor of the amplifier without feedback. So, if the output resistance is small, then less voltage drop will be there at the effective output resistance, and most of the voltage occurs at the load resistance. So, the output circuit will behave like a voltage source. So, if the output resistance is small, then most of the voltage drops occurs at the load resistance. We have to have this kind of action. So, we will calculate the output voltage across the load resistance. So, if we have a major part of the voltage across the load resistance, then that is the desired output. So, we can have a voltage source. So, this particular feedback, the voltage shunt feedback circuit behaves like a current controlled current source, because the input side has smaller resistance. So, we can have a current source, and the output side also have a smaller resistance, and at the output side if we have small resistance, most of the voltage will be seen across the output, and that is what the desired condition for an amplifier also. So, we can have a voltage source at the output. So, finally, we can conclude that the voltage shunt feedback circuit is a current controlled current source. And the next one is current series feedback. So, we have seen the voltage shunt feedback network, for which we have derived the gain, input impedance and the output impedance. And now we are going to see the current series feedback, for which the output impedance will be. You can easily guess the output impedance of the current series feedback, because it is a series type of feedback. So, if it has a series type, the resistances will be added up, and the resistance is increased by the factor of 1 plus beta A. So, you have to derive the same value. And how will you calculate the output impedance? In general, the input source will be equal to 0, that is Vs is equal to 0, and you have to apply the voltage at its output port, and due to the voltage there is a current term resulting in a current term called I. So, by which you have to derive the output impedance. So, this is the general detailed diagram for the current series feedback. So, current has been taken in series and given as the input of the feedback network, and output of the network is again given in series to the voltage source, right. So, here this Vi is equal to Vf, because we have neglected the Vs, we have shorted this Vs, because the general procedure is you have to short the input source and you have to apply the voltage at the output terminal. So, if we short the input source, then Vs is equal to 0. So, if Vs is equal to 0 by the summation part, that is Vi is equal to Vs plus Vf, right. So, if it is 0, then Vi is equal to Vf. And what is I? That is when you apply a voltage at the output terminals, then there will generate a current. That current is given as I is equal to V by Z naught minus AV1. So, this is the output current and this is in opposite to the output current. So, it is minus AV1. V by Z naught minus AV1, that can be equated to, we know that Vi is Vf. So, Vf is replaced for Vi, and what is Vf from this portion you can calculate, it is beta I naught, and replace Vf by beta I naught, and in this case we have taken in general I. So, it is I. So, Z naught, if you simplify this equation, you will be getting this Z out, that is with the feedback, output impedance with feedback equal to V by I is equal to the output impedance multiplied with the factor of 1 plus beta A. So, since we have a series connection at the output, the resistance is increased by the factor of 1 plus beta A. That is what we have derived here. So, for the current series feedback, the output impedance only we have derived, because we have seen the gain of the amplifier and we have seen the input impedance of the amplifier also. And finally, the current shunt feedback. For the current shunt feedback, by look at the circuit itself, we can tell the output impedance is reduced because increased because we have a series connection. We are taking a part of the current output current and given as the input of the feedback network. If you are taking a part of a current, it has to be taken in series. So, you have a series connection. If you have a series connection, the resistance is increased. And for shunt feedback, you have to give parallel to the input of the circuit. So, the output of the feedback network is given parallel to the input source. So, here if it is a shunt connection, you have a current source at the input. So, this is the circuit for the current shunt feedback. So, here output impedance is increased and the input impedance is reduced. So, for this such parameters, the current shunt feedback circuit behave like a current controlled current source. So, since we have increased input impedance, if the output impedance is increased, we know that if you have a voltage source, the most of the voltage will be dropped across the impedance itself, the internal impedance itself. So, we should not have a voltage source here, and so it is a current source, and for the input side the resistance is reduced, and so we have a current source. So, it is a current controlled current source. The current shunt feedback is concluded as a current controlled current source. So, this is the summary part for all the input and output impedances. So, for voltage series, if you look at the summary, if it is a voltage series or a current series, the input impedance is increased because it is series feedback. If you have a shunt feedback, the input impedance is reduced. Similarly, for the output impedance, if it is a voltage, for output impedance, if it is a voltage, the first column and the third column, it is a voltage series and voltage shunt. If it is a voltage, then the output impedance is reduced, and if it is current, then the output impedance is increased. So, this is the effect of the feedback on input output impedances. And next we are going to see the some of the practical feedback circuits. This is for the voltage series feedback. This is a field effect transistor, and there are two potential dividers R1 and R2 at its output terminal, and the voltage across the resistance R2 is taken as the part of the output signal and given as in series with the input voltage source. So, it is a voltage series feedback. So, we have taken voltage, some part of the voltage, and given in series with the input signal. So, it is a voltage series feedback. So, what is the feedback voltage? It is the voltage across the resistance R2. So, feedback voltage Vf is connected in series with the source signal Vs, their difference being the input voltage Vi. So, Vs minus Vf is equal to Vi, that is the actual input given to the FET. So, for FET without feedback, the amplifier gain is minus GMRL, and RL is the output parallel combination of the resistances. So, RL is RD parallel R0 parallel R1 plus R2. So, here if for without feedback, these two resistances are connected in series. So, there is no connection here without feedback, and the output is taken across the drain terminal D, and here you have a resistance RD. So, RD is in parallel with the R0 and parallel with these two resistances which are in series combination. So, that is what RL is RD parallel R0 parallel R1 plus R2. Here R1 plus R2 is because there is no feedback. At that condition, if you take the resistances, it is in series, so it is R1 plus R2. The feedback network provides a feedback factor of minus R2 by R1 plus R2. If you give feedback, what is the gain of the feedback network? So, if you give feedback, then there is a connection at the junction of this R1 and R2, and it is given to the input source Vs. So, here this is the feedback voltage which is given as the input to the in series with the source. So, what is Vf now? According to the potential divider rule, it is R2 into V0 divided by R1 plus R2, but it is given to the negative terminal, it is given here. So, you have to take a reverse polarity. So, minus R2 by R1 plus R2 into V0 will be come here. If you take the gain factor of the feedback network, it V0 can come to the left hand side denominator. So, Vf by V0 is minus R2 by R1 plus R2. Using the value of A and beta, we have A and beta, and we can substitute in the formula gain with the feedback A by 1 plus beta A. So, it is if you substitute these two values minus GMRL minus R2 by R1 plus R2, if you substitute this, and finally you will be getting minus R1 plus R2 by R2, by considering that if A beta is greater than 1, then this AF will be equal to 1 by beta, right. If A beta is greater than 1, you will not have this 1 here, then 1 is neglected in this part. So, A by beta A, so A and A will get cancelled, 1 by beta. So, what is beta? It is minus R2 by R1 plus R2. If it is 1 by beta, you reverse that. So, it is the voltage gain with feedback for the FET circuit. For the current series feedback, it is also again a practical feedback circuit. You have a current series feedback for which you have used a BJT, bipolar junction transistor, and here RB resistance RC and the resistance RE. So, you have taken the output across the collector terminal, and here what is the voltage given as the input, what is the parameter which is given as the feedback to the input signal. It is the output current is taken, but the proportional voltage, the proportional to the output current, the voltage is taken as the feedback signal to its input. So, here it is a current series feedback. Current is the output parameter you have to take, and you have to give it in series to the input from the feedback network. So, that is what here the output current is I0, the proportional voltage across the resistance RE is given to the input side. So, it will be seen across the input side in series with the input signal. So, for which you have to draw the AC equivalent circuit. So, we know that for the transistor, it is a hybrid, approximate hybrid equivalent circuit is at the input side, it is HIE, and at the output side you have a current source it is HFE IB, and this is the approximate hybrid model, and we have neglected the other parameters, that is input impedance and output admittance, and this is your base terminal, this is emitter terminal, and this is collector terminal. To the base we have resistor RB, it is RB, and from the collector we have a resistor RC, and at the emitter we have a resistor RE, which is grounded, and we have shorted all the input sources. If we have a capacitor also, we have to short the capacitor, we have to neglect it, and since we have a capacitor part in the power supply also, we are neglecting it. We have to consider all these as a common points. So, we have just to consider only the resistances and the current forward current transfer ratio, that is the internal hybrid parameters of BJT transistors. This is Vi. So, Zi you have to consider from here, it is Z0, and this is your V0. Okay. So, this is your AC equivalent circuit. So, without feedback, the gain of the amplifier is output current by input voltage. As I said, the output current proportional voltage is seen at its input, but we have to take the parameter as the output current. So, I0 by Vi is equal to, what is I0? I0 is the current flowing at the collector terminal. So, it is minus HFE IB. Okay. So, it is minus HFE IB by this Vi can be written as Vi, this Vi can be written as, this is the base current, IB is the base current, this is I0. So, here IB HIE plus RE, IB HIE plus RE. So, actually IB of HIE plus RE. So, here IB and IB will get cancelled, only it is minus HFE by HIE plus RE. You will have a bracket here, IB into HIE plus RE. So, this 2 IB will get cancelled. So, finally, it is minus HFE by HIE plus RE. And what is beta from the circuit? It is the voltage across the resistance RE. So, it is given as Vf by I0, Vf by I0. So, output, this is output and this is input for this particular network. This is the feedback network now. So, the output of this network is Vf, input of the network is I0. So, Vf by I0, and Vf can be written as minus I0 Re, that is the voltage across the resistance Re. So, this Vf can be written as minus I0 Re because the I0 is reversed when you look at the polarity of the voltage here. So, minus I0 Re by I0, I0 cancel, it will be minus Re. So, what is the input impedance? It is RB parallel HIE plus RE, RB parallel HIE plus RE. And this RB is very low when you compare it with these two parameters RE. So, it is neglected. And what is the output impedance? It is only RC. So, it is the output impedance. So, these are all the parameters without the feedback, and if it is with feedback, if you calculate it, we know what is A, what is beta here, and we know the formula for the gain with feedback, A by 1 plus beta A. So, if you substitute it, it is minus HFE by HIE plus HFE RE. Again you have to substitute in wherever A and beta is available, you have to substitute those values we have calculated without the feedback and calculate what is the parameter, the gain with feedback, the input impedance with feedback and output impedance with feedback. If you look at all these values, it is HFE RE, HFE RE, again it is HFE RE. So, it is increased here. The gain is reduced, the input impedance is increased, the output impedance is increased, because it is a current series feedback. Because series combination, it will increase the resistance, and current also, for current you are taking the parameter in series from the output side. So, if you have a series connection, then the input and output impedances will get increased. And for the voltage gain, actual voltage gain is V naught by Vs, it is given as minus HFE RC by HIE plus HFE RE. The voltage gain is reduced by RE now. So, here the resistance, this resistance is included in this circuit, and so if the resistance is included, the gain is reduced. So, if the gain is reduced, ultimately it cannot be a good amplifier. So, you have to take out this resistance, otherwise you have to bypass this resistance using a coupling capacitor for this circuit to be a good amplifier. This is just a small example for voltage shunt feedback circuit. It is a practical feedback circuit with the operational amplifier, and this operational amplifier has two input terminals, positive and negative terminal. Either terminal can have a input signal, and only at the negative terminal we will have a feedback voltage. So, here the input is given to the negative terminal through the resistance R1 and output is fed back to the negative terminal through the resistance R0. Always the assumption for the input side of the op amp is input current is 0 and input voltage is 0, and voltage gain V naught by Vi is always infinite. And when you calculate what is beta, beta in this circuit is IF by V naught, because IF is the current flowing through the resistance and V naught is the output voltage given as the input, part of the output voltage given as the input. So, beta can be written as the current by V naught, IF by V naught, and it is IF by V naught is minus 1 by R naught. For the voltage shunt feedback, the feedback network's gain is IF by V naught. So, if you look at the circuit, the value of IF by V naught can be written as minus 1 by R naught, because the current through the resistance is reversed when you look at the output voltage. So, it is minus 1 by R naught. The gain with feedback is with the feedback. So, you have seen what is A and what is beta for the voltage shunt feedback. The gain with feedback AF is A by 1 plus beta. You substitute the values, you will have the result as minus R naught. So, this is just the transfer resistance gain. Actually, the voltage gain with feedback is calculated from V naught by Is into Is by Vi is minus R naught into 1 by R1. So, the gain of the overall voltage gain of the amplifier is minus R naught by R1, that is the feedback resistance by the input resistance R1. The next topic is phase and frequency considerations. So, for an amplifier, the feedback may be a negative feedback or a positive feedback. If it is a negative feedback, then the output will reduce the feedback signal will reduce the input and finally the output and finally the gain. If it is a positive feedback, then the input aids the feedback signal aids the input signal. So, here we will see how the positive feedback affects the amplifier and how the amplifier has to be stable, and what are all the methods for determining the stability of the amplifier in phase and frequency considerations. We will see it in the next class. So, in this class we have seen that the derivation of the gain, input impedance and output impedance of some of the remaining feedback circuits, and practical feedback circuits in which we have seen the voltage series, current series and voltage shunt feedback. Some questions: draw the op amp circuit with voltage shunt feedback and derive its voltage gain. Draw any practical current series feedback circuit and derive its gain, input and output impedances. These are the references. Thank you.